Hi, welcome to CDA 5220. Today I will talk about the supplementary material that contains cache animation to illustrate better the concept of a cache memory. And a lot of these slides were contributed by my former colleague at NC State, Dr. Eric Rothenberg. So kudos to him. So we will start with the cache parameters. So sometimes people call this ABC. A stands for associativity, or the number of blocks in a given set, or the number of columns. And then B for the block size, the number of bytes that can be held in a single cache block. And then C for the cache size, or the total amount of cache data storage in number of bytes. So you notice that there is one missing parameter, which is the cache set, or number of sets. It turns out that the number of sets can be derived by using these other three parameters. And let me explain. So in order to obtain the number of blocks in a cache, we can divide the cache size with the block size. Okay. And then when we want to find the number of sets, we can further divide the number of cache blocks with the associativity. Or if we combine the two formula together, what we will find is that it will be C divided by AB, right? So the cache size as the numerator divided by block size times the associativity. And knowing the number of sets, the cache block size, and this helps in learning how an address is used by the cache. So let me explain. Suppose we have a 32-bit machine. That means every load and every store instruction will provide an address that is 32-bit long, and we have to figure out how is are these bits used by the cache. So we will see that the middle bits is called the index. This will be used in order to find the number of set, right? So it is used to look up a set which contains one or more memory blocks. This is because of the placement policy of a cache, that given an address, it has to map to a unique set. Now, however, the main memory is much larger than a cache, so there are a lot of there are a lot of blocks that map to the same set. So therefore, we have to remember which blocks are currently kept in a cache, and we have to compare, or we have to have a way to know if the requested address actually maps to a block that is currently cached. And that is performed by using the tag. Okay, so when the load and store provides a tag, provide an address, the tag bits are going to be used for comparison against the tags that are stored in the cache. If the tags match, it indicates that we have a cache hit, so the block that we want is actually in the cache. But if they don't match, that means we have a cache miss, meaning that the block that we want is not currently cached, so we have to find it in the main memory. Now, if we have a cache hit, then we have to return the correct bytes or word, depending on the granularity of the store or load, to the processor. And for that, we will use the block offset bits. And how are these bits calculated? Meaning, like, how many bits are used for the different fields? And this will be computed using the width of the address. So the number of index bits is simply the log 2 of the number of sets. Okay. Log 2 is just basically a logarithm with a base 2. Now, block offset bits will be computed as just a log 2 of the block size, and the tag bits is basically whatever is left over, meaning that we start with the 32 bits, which is the total width of the machine, and then we subtract the number of index bits and subtract the number of block offset bits. Now, once we determine the size of each field, we can look up the cache. So here's an example of a direct map cache. So there's only one associativity, so there's only one column. And we have a data array right here. And we have a tag array that basically keeps track of which block is currently cached in each of the set. So we will start with the index bit. So we use the index bit to find out a specific set that this address maps to. And then we read out the tag and compare the tag against the tag that is requested by the processor, by the load and store, to determine whether we have a hit or a miss. If we have a hit, then we also read the data block from the set that was activated, and then choose the correct bytes or word using the block offset bits, and then return that to the processor. Okay, let's look at an example. So suppose a processor accesses a 256 byte direct map cache, and let's say the block size is given as 32 bytes. And we will provide a sequence of addresses, and what we have to find out is what happens with the cache with regard to how many cache hits occur, how many cache misses occur, and how many replacements occur. So here is the address sequence that are given. Alright, so remember that we have a 32-bit address, and on the first column here we see these 32 bits encoded in hexadecimal, meaning that each bit, each digit corresponds to 4 binary digits. Okay, so we're gonna call that a nibble. And because they are 32 bits, if we divide by 4, we get 8 nibbles. Okay, so you can see there are 8 digits in hexadecimal. So FF0040E0, there are 8 digits there that corresponds to 32 bits. Okay, now we need to figure out what of this, of this address, which bits correspond to the tag, which bits correspond to the index, and then we have to find out what happens. Do we have a cache hit, cache miss, a replacement, etc. Also, to help us, we're going to convert the index value from binary to decimal, just for making it more human friendly, but the meaning is the same. Okay, so let's start. First, we need to figure out how many bits are used for the different fields. So first, we will use the formula to calculate the number of sets. In this case, we divide the size by the block size and associativity. So we divide 256 by 32 and by 1, because it's a direct map cache. And we find it's 8. So there are 8 sets in the whole cache. And now we are ready to find how many bits are used for the index, which is basically the log 2 of the number of sets. In this case, the log 2 of 8 is 3. So we use 3 bits for the index. And then for the block offset bits, we take the log 2 of the block size, which is 32 bytes, which means we use 5 bits for the block offset. Now the number of tag bits that are used is basically just whatever is left over, which is 32 minus 3 bits minus 5 bits, which gives us 24 bits. So we can see that here we have the top 6 nibbles, which is top 6 digits, form the tag, and then the lower 2 nibbles, which is 8 bits of the address, will form a combination of the index and the block offset. Okay. Now if we calculate that, this is what we will find. So the first 6 hexadecimal digits correspond to the tag, and the last 2 bits, which is in this case, for example, E0, and then if we convert that to binary, we will see 11100000. And of these 8 bits, the upper 3 bits is the index. So for example, 111, this is shown in red. That's the index bits, and the corresponding decimal value is 7. And then the block offset bits is the leftover, which is, you know, the black digits, right? So 0, 0, 0, 0, 0. All right, so now we have partitioned the addresses into tag, index, block offset. Now we can look at the cache, what happens to determine whether we have a miss, hit, etc. So here in the last column, I give you the answer already, but let's figure out through an animation of what happened. All right, so again, we see that we have the 32-bit address, and then the first 5 bits will be used for block offset, the next 3 bits for indexing, and the last 24 bits for tag. Let's start with the first address that is accessed. It has an index value of 7. That means we go to the cache, activates the decoder to read the last set in the cache. So we read the tag and the address portion. So the block that we want to access has FF0040, and we're going to compare that against the tag that is read from the cache. And in this case, we have a mismatch. So we have a cache miss. So we have to fetch the data from the memory and bring it to the cache. All right. Next, we access an index 2. We activate row number 2. We read out the tag and compare it against the tag that we want to access. In this case, BEEF00. We compare that. And since the tags do not match, that means the cache doesn't have the requested block. We have to bring it from memory. And when we bring it from memory, we place the data block, but also we record the tag that this is the block that we currently keep in the cache. Next, we have index 7, and we activate the set number 7, read out the tag, and the requested tag is FF0040, which turns out to match. So in this case, we have a cache hit. Now we have an access to index 3. In this case, we will read out set number 3, and the requested tag is 001010, and we compare the tags and they mismatch, and therefore we have a miss and we have to bring data from memory. Next, we have access to index 7, so we read out set number 7, and the tag that we want to compare is that we want to access is 002183, which mismatch with what we have in the tag. That means that the block that we want is not in the cache. So therefore, in this case, we have a cache miss, and we have to replace the existing block. There you go. Next is we have access to index 3. We read out from the tag array, and the block that we want to access turns out to have the same tag. So we have, in this case, we have a cache hit. Moving on, we have an access to index 2. We read out index 2, and it turns out the tag that we want to access is not this. So that means the block that we want is not cache, so we have to bring it from the main memory and replace the current block. Our final access to index 2 again, and in this case, what we want to access is tag 001225, and when we compare the tag, we have a cache hit.